Managing a modern power grid requires millions of variables. Engineers rely on power system analysis to run predictive models of these massive networks, testing steady-state load flows and mapping exactly how quasi-steady-state fault currents will behave if something breaks. To handle the mathematics of networks this vast, they strip away the actual kilovolts and kiloamps. Instead, they use the per-unit system, a simplified standard that divides actual electrical quantities by a chosen base value, representing everything as a unified fraction. By converting a whole grid to this standardized per-unit scale, engineers can simulate complex short circuits entirely in software, testing the limits of the system long before the physical equipment is manufactured. Yet, despite having these highly standardized, mathematically rigorous models, the way actual faults behave out in the field routinely contradicts basic human intuition. Logic suggests that if an event severs all three main high-voltage transmission lines simultaneously, that three-phase short circuit should produce the maximum possible, most destructive surge of current. Curious, leaning in, but this chart shows a different reality. In many practical power systems, a single line-to-ground fault, where only one wire breaks and touches the earth, actually generates a significantly higher surge of current than a complete three-phase failure. It is entirely counterintuitive. You have to ask how a single severed connection can channel more raw destructive energy than three severed connections combined. This surge stems from an internal property called zero-sequence impedance, or Z0, located deep within the magnetic core of the power plant's machinery. To figure out why the grid fails the way it does, we have to look past the macroscopic network maps and examine the microscopic magnetic physics of the machines powering it. Every surge of power originates inside a synchronous generator, the physical site where this anomaly is born. Normally, the generator runs in a balanced state. The three electrical phases push against a continuously rotating magnetic field inside the machine. This normal state produces a high natural resistance to the flow of current, which engineers call positive sequence impedance. During a single line-to-ground fault, the three staggered alternating current sine waves shift. They align perfectly in phase, pulsing in absolute unison. Because they are synchronized, their internal magnetic vectors cancel out, generating only minor magnetic leakage instead of a strong rotating field. The machine loses its primary mechanism for restricting current, the magnetic back pressure of its own rotating field. This leaves only the generator's small internal leakage to stop the electrical flow, allowing the fault current to move almost entirely unimpeded. Relying solely on small internal leakage paths to slow down electricity, the generator's zero-sequence impedance plunges to a fraction of its normal operating level. This establishes a strict mathematical hierarchy inside the machine. The generator's zero-sequence impedance is vastly lower than its negative sequence impedance, which itself is far lower than the standard positive sequence value. Contrast that with standard transformers out in the yard. A typical delta star transformer has a zero-sequence impedance that sits right around 90 to 110% of its positive sequence value. This severe structural lack of resistance is an inherent flaw unique to the generator itself. With its zero-sequence impedance sitting so low, the generator acts as an enormous unintended funnel. It creates a path of least resistance specifically tailored to amplify single line-to-ground faults. When that single high-voltage transmission line snaps and strikes the earth miles away, the generator's internal funnel is thrown wide open, causing the fault current traveling back through the ground to spike violently. Power engineers cannot rewrite the laws of magnetic flux dictating the inside of the generator. To protect the grid, they have to control the external environment outside the plant. They manage this threat by manipulating a single crucial variable, system grounding. This circuit model illustrates the two primary defense strategies. On the left, solid grounding creates a direct connection to the earth, allowing that maximum single-line fault current to flow so protective relays can easily detect it. On the right, resistance grounding inserts a physical resistor into the neutral path, which deliberately chokes the flow and limits potential hardware damage. Leaving the system completely ungrounded chokes off the zero-sequence fault current almost entirely. But it traps the energy in the system, risking violent, catastrophic overvoltage arcing right across the expensive equipment. Zero-sequence impedance acts as a physical dictator of the grid, forcing engineers to constantly balance catastrophic current levels against explosive voltages.